Alright, what's up guys? In this video, I'm going to pick up some multivariable calculus. Going to be talking about triple integrals and spherical coordinates. So as to evaluate the triple integral here, where f of x comma y comma z is equal to z multiplied by x squared plus y squared plus z squared, all raised to the negative 3 over 2 over part of the ball given by the following equation, x squared plus y squared plus z squared is equal to 4. So basically what we're looking to do here is to set up our triple integral, but we certainly don't want to evaluate this in cylindrical coordinates. We need to convert to spherical coordinates, and certain integrals, and we've seen this with the doubles, have to be integrated in certain coordinate systems. That's just the way it is. But although you may not realize it, changing coordinate systems in most cases actually makes the integration simpler. I mean, can you imagine trying to evaluate this triple integral in cylindrical coordinates? It wouldn't be fun. So that's the purpose of switching things, sometimes switching it over to spherical, or even with the doubles, doing things in polar coordinates sometimes may be a lot better than doing it in Cartesian coordinates. Okay, so all you really need to remember about spherical coordinates and how we go about this is pretty simple. Let me just quickly remind you. Alright, so for spherical coordinates, remember that rho squared, that's going to be x squared plus y squared plus z squared. Remember that x, that's going to be rho sine phi multiplied by cosine theta. On y, it's going to be rho sine phi sine theta, and our z is going to be rho cosine phi. Now, in our particular circumstance, when we look at the part of it says here that we have a part of a ball given by the following. Well, we know that essentially we can convert that into spherical coordinates. Now, since rho squared is equal to x squared plus y squared plus z squared, and we can see here that we get 4. Well, what value can I square and get 4? Well, I can square 2, which means that rho is 2. So we know the ranges now for rho, and we already know what the ranges are for phi and theta anyway of spherical coordinates. So the ranges in this particular circumstance, or the restriction coordinates basically, for rho are going to be, well, rho is going to be in between 0 and 2. Phi, it's going to be in between 0 and pi, and then theta will be in between 0 and 2 pi. So those are going to be our ranges. And remember for, I guess I'll do it down here. Remember for spherical coordinates, it's going to be rho squared sine phi d rho d phi d theta. All right, so hopefully that made sense. So now we just kind of got to go through, do the substitution process, clean it up a little bit, and we should be able to get started with the integral shortly. Alright, so the integral now is going to be from 0 to 2 pi. It's going to be from 0 to pi. Then it's going to be from 0 to 2, because remember we're integrating expect a rho first, so make sure you're lining up the ranges with the correct differential. So if we convert to spherical coordinates, well, that means that we'll have rho cosine phi. I'm going to put rho squared in parentheses because it's being raised to the negative 3 over 2. We'll simplify that in a minute. Don't forget about that other rho squared that was in there. And then we still got sine phi. And again, it's going to be d rho d phi d theta. Now, we've converted this to spherical coordinates. And again, it may not seem like this helps at all. I mean, maybe this looks a nightmare to you guys. For some of you might not. You might be good at triple integral. It might not be a nightmare to you at all, but it does look like it's very complicated here. But there's really not a whole lot going on here. All we need to do is really simplify a little bit of this and kind of clean it up, and it just becomes a triple integral at that point. So it's not as bad as it appears. Let's just kind of deal with some of the simplification. So notice that we got a row here, and then we got another row. So if I multiply row by row squared, I'll get row cubed. Now we could take care of this part. So I have row squared all raised to the -3/2. Well, if you're like me and you like positive exponents, it would just be 1 over row cubed. Now I have a row cubed there, I have a row cubed there, which are actually going to cancel out, which will leave me with 1 times cosine phi sine phi, which would just leave me with cosine phi sine phi, which I'll need to integrate. So now the triple integral becomes from 0 to 2 pi, from 0 to pi, and then from 0 to 2. Now the integral just simply becomes cosine phi multiplied by sine phi. And again, it's going to be d rho, d phi, d theta. So we've cleaned it up. So, all right, so just got to deal with the triple integral. So I just did a video a second ago on triple integrals. So they're not, triple integrals, in my opinion, are actually harder to set up than they are to evaluate. Most triple integrals, believe it or not, now obviously that can vary, but most triple integrals as it pertains to evaluating isn't really too terrible. I mean, you very rarely, I mean, sure, it could happen, run into instances with these triple integrals where you're applying a whole bunch of different integration techniques. It just doesn't happen very often. So a lot of these triple integrals, they actually aren't that bad once you actually get down to the whole integration thing. So since we're integrating with respect to rho first, so we got cosine phi, sine phi, integrated with respect to rho first. So that means we treat the other two variables as constants. And you work your way from the innermost to the outermost integral. So since we're integrating with respect to rho, that means that cosine phi and sine phi are constant, or we treat them as constants. And it's going to be multiplied by rho. Since we're integrating with respect to rho, and it's going to be from 0 to 2, which will get me down to my double integral at that point, which is going to be from 0 to 2 pi, from 0 to pi. And when we do the substitution in here, we'll have cosine phi times sine phi times 2, which would give me sine of 2 phi. So this would be sine of 2 phi. And it's going to be d phi, d theta. So we're now integrating with respect to phi. So this is going to be from 0 to pi. And we got sine of 2 phi integrated with respect to phi. Remember that the antiderivative of sine of 2 phi is just going to be -1/2 cosine of 2 phi. And we'll need to evaluate that from 0 to pi. Okay, so remember that cosine of 2 pi is negative, no, cosine of pi, oh, I'm having a brain fart. Oh, yeah, hold on a second. Yeah, -1. I wanted to say -1, but I don't know why I was guessing myself. So basically, when we stick in a pi here, we'll simply get -1. Now, don't forget about the -1/2 over here on the side. So essentially, what we'll end up with is -1/2. Now, cosine of 0 is 1, but we do have a -1/2 here. So essentially, what we're really dealing with is cosine of 0, which is obviously 1, multiplied by -1/2, which would give me a -1/2. So essentially, what I'd have is two subtractions. So I would have minus 1/2, which essentially becomes plus, and this will obviously give me a 0. Whew, sorry, I had a brain fart up there earlier. I was like, what the heck is cosine of pi? It's -1. So sorry, it's been a long day. Okay, all right, so now we're just left to integrate from 0 to 2 pi, and we're just integrating a constant with respect to theta, and obviously that is just simply 0. And that's your final answer. And that's going to be your final answer. Your final answer is going to simply be 0. All right, so hopefully I was able to help you out with that. And like I said, feel free to reach out if you got any questions about how I got my answers. I'll be more than happy to specify it. All right, I'll see y'all next time.